Over the years, there have been significant advancements in reconstructing opaque objects, with techniques like NERF producing amazing results. However, transparent object reconstruction still remains a challenging problem. Transparent objects introduce additional complexities such as refraction and reflection, making their reconstruction more challenging compared to opaque objects. Previous attempts at transparent object reconstruction required the use of manual annotation or the use of darkrooms to obtain object silhouettes. In the paper, Transparent Object Reconstruction via Implicit Differentiable Refraction Rendering, the authors present a new approach that offers a simplified and automated process to reconstruct transparent objects in unknown natural scenes while only using multi-view RGB images as input. Their approach consists of two key aspects. First, generating accurate silhouettes of the object for each view, and secondly, reconstructing the object and refining it using implicit differentiable refraction rendering. For the first step, they introduce a neural network called the scene network, NS, which maps a 3D location and its view position to a view-independent sign distance and the view-dependent color. The network is used to represent the entire scene, including the transparent object. However, while the representation of the plane the object sits on is sufficiently accurate, the representation of the transparent object is not as accurate due to what they call shape radiance ambiguity. The ambiguity arises because essentially the object looks different from different viewing angles. To address this, they use the information from the sign distance field of NS to estimate its silhouette. The silhouettes are crucial because they provide strong constraints for the shape reconstruction step without the need to consider the color values of the object. To estimate the silhouette, they start by tracing the rays through the scene. The weight of each ray is determined by the position along the ray's path, where a weight of 0 means the position is in open air and a weight of 1 means the ray has intersected with the plane or the object. Then with these weights, they define a silhouette function Fm, which integrates the weight of each ray, and by setting a threshold sigma, they can determine if a ray has hit the object, resulting in a more accurate silhouette than if they got the reconstruction just from the scene network. Now with some initial shape constrained by the silhouettes, we can further refine the reconstruction with the use of the actual light paths that are refracted through the transparent object. This is where they introduce another network called the object network, or NO. This network only outputs the sign distance field of the object rather than the whole scene like an NS. With this SDF, they implement the process of implicit refraction rendering, where the goal is to determine the color of each ray through the object in order to make assumptions of the geometry by enforcing the color of the refracted ray to be consistent with the actual input image. This involves tracing the ray until it intersects with the transparent object at x hat. Then by using the gradient of the SDF at x hat, we can determine the normal vector of the object. The refracted ray is then calculated according to Snell's law and the object's index of refraction. Then we can determine the final color of the ray using a point on the estimated texture of the plane from NS. For the ray sampling process, their goal is to efficiently use the estimated silhouettes to constrain the object's shape without calculating the silhouette loss for each of the rays. Instead, they only sample rays close to the silhouette edge, as they're most important for constraining the silhouette. After testing their methods on synthetic data, such as renders, we can see that this method still skips over some details, like the eye of the tiger here. But they still preserve more detail than previous state-of-the-art methods, such as the folds of the tiger belly here. The process for one object takes around 4 hours on a single RTX 4090 for shape reconstruction, and a total of 11 hours for the whole process when they have around 40 to 50 RGB images. Although the method produces high-quality results, there are some limitations in recovering the contact regions between the transparent object and the plane, as seen in this image here. The limitation arises because there are fewer refraction distortions on these parts that are closer to the plane. In conclusion, transparent object reconstruction has long been a challenge in computational photography and computer graphics, but this novel approach, presented in this paper, offers a simplified and automated solution. By generating accurate silhouettes with the scene network, and by refining the reconstruction by employing implicit differentiable refraction rendering, this method is able to accurately reconstruct transparent objects in natural scenes while only using RGB images as input. I hope you learned something from this video, and thanks for watching.